Good afternoon, everybody. Today we're going to be talking about section 2.3, techniques for computing limits. So we saw earlier in section 2.2 that we can compute limits graphically and we can compute them using a table. But what are some other techniques for computing limits that might make our life a little bit easier? And that's what we're going to talk about today. So these are all going to be called limit laws, and they're going to make our lives really easy. So the first limit law we have is the sum limit law. And this just means that the sum of two functions, a function f of x and a function g of x, the limit of that sum is equal to the sum of the limits. That is, the limit as x approaches a of f of x plus g of x is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. And if it's true for the sum, then it must be true for the difference. So all we did was change the sign here and here, and we get the difference law. So the sum and difference law make our lives really easy. The next limit law is the constant multiple law, and we'll see this used a lot, and you'll see this used in a different fashion later on in the semester. So let C be a constant value, i.e. one that does not depend on x. So maybe we've got 6 times x, maybe we've got 6 times x squared, maybe we've got 15 times x. That 6 or that 15 is definitely going to be what we call C, and we can pull it out of our limit. So our first limit is the limit as x approaches a of C times a function f of x, and it's equal to C times the limit as x approaches a of f of x. The next limit laws we have are the product and quotient limit laws. And a product is just two functions multiplied together. So we have f of x times g of x, and we want to know the limit as x approaches a. And it's simply just the limit as x approaches a of f of x times, I've suppressed the times symbol, the limit as x approaches a of g of x. And if it's true for the product that we just multiply the two independent limits, then it must be true for the quotient. So indeed, we see that f of x, a function divided by g of x, assuming g of x does not equal 0, the limit of that entity as x approaches a is the same as the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. And this is all assuming that g of x, let's see, the limit as x approaches a of g of x does not equal 0. And that's a pretty important part because we know we can't divide by 0. Finally, we have the power rule and the root rule. So let n be some positive integer. And an integer is just a whole number including 0. So we have plus or minus 1, plus or minus 2, etc., etc. So the limit of x approaches a of f of x to the power of n is the same as the limit as x approaches a of f of x quantity to the power n. So all we did was pull that out. And we know this to be true because if we see an example where n equals 2, and we say the limit as x approaches a of f of x squared, well, that's just the same as the limit as x approaches a of f of x times f of x. And we can break that down even further using our power rule or our product rule from previous. Now, if it's true for a power rule, then it better be true for a root. So the limit as x approaches a of f of x quantity to the power of 1 over n, then it's true that the limit is equal to limit of f of x as x approaches a quantity to the power 1 over n. And it's true for the exact same reason as the power rule is true. So let's go ahead and use these in practice and see some examples. So in this example, we're going to suppose that the limit of f of x as x approaches 2 equals 4, the limit of g of x as x approaches 2 equals 5, and the limit of h of x as x approaches 2 equals 8. And we're going to use our limit laws to compute the following. So the very first one we're going to do is the limit as x approaches 2 of f of x minus g of x quantity divided by h of x. So we know we can rewrite this using our quotient rule as the limit of our numerator, f of x minus g of x, divided by our denominator, which is the limit of h of x. And for ease of use, I'm just going to suppress the x approaches 2 notation just to keep everything clear. So we can simplify the numerator even further because we've got a difference in there. So it looks like the limit of f of x minus the limit of g of x all over the limit of h of x. So now all we have to do is plug in the values that we have up here. So the limit of f of x as x approaches 2 is simply 4. The limit of g of x as x approaches 2 is 5, so we've got 4 minus 5 over the denominator, which is going to be 8. 4 minus 5 is -1. Our limit is -1 over 8. And I'll go ahead and draw a line like that. So now let's talk about b, and you can probably work through this one on your own, but just in case, let's go through it together. We've got the limit of 6 times f of x times g of x plus h of x as x approaches 2. So first, let's rewrite this as the limit of 6 f of x times g of x plus the limit of h of x. And here we can separate and pull out that 6. So we get 6 times the limit of f of x times the limit of g of x plus the limit of h of x. So now all we have to do is plug in those final numbers. So we've got 6 times 4 times 5 plus 8. So 6 times 4 is, well, 6 times 5 is 30. 30 times 4 is 120. So our total is 128. And finally, we are just interested in the limit as x approaches 2 of g of x cubed. And that's the same as the limit of g of x quantity cubed. So g of x is 8, so it's equal to 8 cubed. And I'm not going to compute that because I don't know it off the top of my head. But that's how we use our limit laws. So there's a little bit more to this lecture left. But if these feel shaky, go ahead and review them, work on the homework problems, shoot me an email, and we can do some examples in office hours if you need. So finally, let's talk about polynomials. Now, polynomials are probably the most frequent algebraic item that we come in contact with, or algebraic object. And a polynomial is going to take the following form, with a sub I are real numbers, possibly 0, and x to the power j are powers of our variable x. So we've got a sub n times x to the power of n, plus a n minus 1 times x to the power n minus 1, plus all the stuff in the middle, plus a1 times x to the power 1, which is just x, plus a0 times x0. So note, y equals mx plus b is a polynomial. And in this case, I'm going to write it in red. M is equal to a1 and b is equal to a0, right? So we are used to seeing polynomials, just maybe not in this form. So if this form confuses you, shoot me an email and we can break it down a little further and I can give you some more examples. The only thing you have to remember is that anything to the power 1 is itself, and anything to the power 0 is 1. Now, if we have a polynomial, well, then we can do something pretty special. So let's assume that P and Q are polynomials and let A be some constant. Then the limit as x approaches A of P of x is the same as just plugging in A. And you can use your limit laws to compute that. Finally, if you've got one polynomial divided by another polynomial, otherwise known as a rational function, then we just get to use our quotient law, right? So instead of jumping through hoops, all we have to do is, again, plug in a into the numerator, plug in a to the denominator, and as long as the denominator evaluated at a point a is not 0, then we're good to go and we can compute our limit. So let's go ahead and see an example. So this is example 2. Evaluate the limit of p of x as x approaches a, where p of x equals 7 times x cubed plus 3x squared plus 4x plus 2. And you'll see, based on my definition of a polynomial that I gave in a couple slides previous, this is indeed a polynomial. So the first thing we get to do is just, well, let's use our limit laws to separate this out. So I'm going to skip a few steps, but the limit is going to be 7 times the limit of x quantity cubed plus 3 times the limit of x quantity squared plus 4 times the limit of x plus 2. So 2 is constant, so we don't plug in any x or any a. It doesn't change at all. So all we have to do is leave it as it is. So now we're going to go ahead and plug in a. And in this case, we just have to plug in a. A isn't any sort of value. So we get 7 times the limit of a cubed plus 3 times the limit as x approaches a squared plus 4 times the limit of a plus 2. Now, because this is a polynomial, the limit as x approaches a, all we do is plug in. So we're left with 7a cubed plus 3a squared plus 4a plus 2. And that's our final answer. I've got one more example for you, and then we're going to be done for today's lecture. So this is evaluate the limit as x approaches 2 of 3x squared minus 4x over quantity 5x cubed minus 36. So again, all we have to do is plug in the number 2 and check that our denominator doesn't equal 0. So our first step is plugging in 2. And this looks like 3 times 2 squared minus 4 times 2 all over 5 times 2 cubed minus 36. So let's do some quick maths. 2 squared is 4 times 3 is 12. 4 times 2 is 8, so we have 12 minus 8 in our numerator. 2 cubed is 8 times 5 is 40 minus 36. We know that's not going to be 0, so we've got 4 in our numerator, 4 in our denominator. Our answer is just the number 1. And that's as easy as it gets. All right, I'll see you next week for sections 2.4 and probably 2.5. Have a good weekend.